So it's a pleasure to be here. When I was approached by Charlie on this, he said, look, you can be provocative, you can try, go for the heaven. So indeed, I'm going to suggest that the information we have about the universe, there's always been a component we have lost in the equations, and that's entropy. That's information. I'm going to try to convey to you that information or entropy gravitates, so it modifies the structure of space-time. It's not just matter and energy, like Einstein told us, but also information, which changes the paths of particles. So this is work that I've been doing with my student, a PhD student, Llorenç Espinosa, actually the same origin as the philosopher we just heard of, in a succession of papers. And together with Arjona and Salas-Neseris, where we looked at the effects that these ideas, this theory has on observations of our universe today, whether we can understand the cosmic acceleration of the universe in terms of this theory. So I'll go to basics first. We're all familiar with fundamental forces, gravity, electromagnetism, the strong and the weak nuclear forces. We're familiar also with the residual forces of these, for instance, molecular forces, or the nuclear energy, nuclear banding energies that keep together nucleons in the nuclei. These are residual forces, but there's an extra, there's a third classification of forces, which are collective forces. These are forces that arise because you're in systems which are very complex, some of which you coarse-grain over, and they describe the physical system in terms of a few extensive parameters like temperature and entropy, but they do contribute with a force. This is something we're very familiar with in Brownian motion, and very simply can be described with the second law of thermodynamics in a very simple way. This is the work that you do on a system where there is some internal energy and there's some entropy. Now, the second law of thermodynamics tells you that these two quantities should be related. So if you work out what's the force on a system where there are gradients of internal energy or there are gradients of entropy, you see that there are these two forces that arise. And it's this force which determines the motion of Brownian particle affected by the thermal motion of the molecules in which it inhabits. Now, this also happens at the level of the universe. So entropic forces are responsible for the present cosmic acceleration, as I will try to put forward to you. This is our proposal. But not only this expansion that we measure today, that we ascribe to a vacuum energy, or claim that there is no such thing. It's actually an entropic force, but also it affects logical structure formation. It affects how the cosmic web forms, how the entropy enters or arrives to a cosmic void, and how that changes the way galaxies move in our universe. There is obviously a need in this context of a covariant formulation of out-of-equilibrium phenomena in general relativity, which it wasn't there until we proposed it. And I insist here, this is really from first principles. I'm not introducing any new concept, but all the laws that we know of: gravity, thermodynamics, and quantum field theory. So how does this go? Well, we know general relativity is a time reversal invariant. So if you go t to minus t, you still have the same theory. And this is true for most all the fundamental theories, except for CP odd theories like the electroweak theory of particle physics. Now, this means that most of the history of the universe is expanding quasi-adiabatically or quasi-isentropically. This is true as long as there is local thermal equilibrium and we don't have production of particles. So it doesn't count for the tremendous explosion of the creation immediately after inflation, where you reheat the universe and you enter into the radiation era. There you do have clearly a production of particles of entropy and clearly an hour of time. Now, irreversible phenomena were typically not included in GR in a systematic way, and I'm going to try to use some of the concepts that were derived actually not that long ago by two people, Guy Balmas, a Frenchman, and Yoshimura, a Japanese, in 2017, who did the variational formulation of non-equilibrium thermodynamics in the context of classical mechanics. And we're going to extrapolate this, or we're going to generalize to the theory of general relativity. And the basic concepts are the laws of thermodynamics, the stationary action principle, which give rise to a constraint dynamics. Okay, this is a constraint that we have to keep on the general setup. And this will define a new variational problem. Seen like this is very abstract. Let me be more concrete. So how do entropic forces appear in mechanics? Usual classical mechanics. So in this system, if you have a canonical coordinate q, this could be the position and its derivative, its velocity of the Brownian particle, and it's immersed into a plasma or a collection of bodies with a given temperature and entropy. The Lagrangian of such a particle, with which you build your action, will have a variational form, which will give you the usual Lagrange equations of motion, but you have to take into account that this is embedded into a system where there are those rapid degrees of freedom which can only be coarse-grained and give rise to the temperature and entropy. And as long as you add to this evolution a thermodynamical constraint, so you make sure that whatever variation you have of entropy in the system should be compensated by a variation in the position of that particle, in particular in the form of a force. This will give rise to constraint equations of motion. So here are the usual Lagrange equations of motion, and you supplement this with a friction or entropic force. This force will change the evolution of the system due to the presence of those degrees of freedom that they have coarse-grained over. Now, what is the physics of this force? It has to be determined clearly from the thermodynamical constraint. So normally in a system where you have the matter Lagrangian in terms of the entropy, you can compute this quantity, the variation. This gives a definition of the temperature. And if you substitute here and you ask for entropy production, so it's a system which through its evolution is going to grow in entropy, this means necessarily this function should be negative. Now here notice that it appears, because of the thermodynamical constraint, a clear breaking of a time reversal invariance. So the dynamics now is modified, it's no longer time reversal invariant. There is, due to this entropic force, a breaking of the symmetry. Now, generalizing this to general relativity, it's not quite straightforward, although it may look like it. Notice that typically you have the gravitational action. You supplement this with the matter action. In the matter action, you assume that all your degrees of freedom are well defined together with the metric, and then you work out the Einstein equations. Now here you have another component, and that's the entropy. This is the entropy of those degrees of freedom that you're not counting over. You've been coarse-grained over. And these degrees of freedom also contribute to the variational of the action in the variational principle. As long as you add here the variational constraint, the second law of thermodynamics, written in this way, then you find a new set of equations beyond the Einstein field equations, which contain on the right-hand side the matter part of the Einstein equations, the one you derive from the Lagrangian of matter with respect to the metric, but there's an extra term. This is the entropic force. This, together with the Bianchi identities, which tell you that the left-hand side of the Einstein equation should, its covariant derivative should be zero, immediately tells you that the energy content, this covariant derivative cannot be zero. It must be related to the growth of entropy. So here you have the origin of the force that is going to affect, as I will describe in a minute, cosmic acceleration of the universe with the same matter content that we believe it is there. Let me go forward. Yeah. Now, the way to see this more explicitly is by doing an ADM Formalism splitting, so 3+1 splitting. This is your element, line element, in terms of coordinates, time, and x. The lead derivative along the normal vector. So you define this 3+1 splitting, a spatial hypersurface, a normal to that hypersurface, characterized by this vector n alpha. The metric hij can be projected out from transfers to the metric along the transfers to the normal vector. And this lead derivative would be a generalization of the time derivative. So you can work out the extrinsic curvature. You can work out also the thermodynamical constraint in those in that language. This force ij is nothing but the projection over the three-dimensional surface. You can derive the Hamilton equations very simply. The only term extra that appears with respect to the usual formulation is this one. In the Hamiltonian momentum constraints, the fact that this should be zero means that there is an extra term that will come here from the entropy contribution. And this is not modified. Now, Let's think now further into a congruence of geodesics. So not only do I do a 3+1 splitting, then I ask, how would a congruence evolve in size, so the trace, theta, in shear, in the form, in the shape, sigma, and in vorticity, the rotational properties of that world line congruence. I assume for the moment that n nu doesn't have to be necessarily the co-moving velocity, so we can in principle have some accelerations. If you compute now the least derivative with respect to the trace, theta, you get to the first Raychaudhuri equation, a very famous equation, where you see first that it depends obviously on the rate of expansion squared of that volume, on the trace of the shear component, the trace of the vorticity, and here it depends on the matter content. Now, when you substitute the equation, the Einstein equations, which are modified by the friction term, which goes beyond the energy momentum tensor, and assuming that these two quantities are positive, which they are, and vorticity vanishes, here we're assuming this normal vector. For instance, we can assume that there's no intrinsic acceleration, the normal vector is just a moving vector. And taking the Einstein equations and writing them this way, if you satisfy the strong energy condition, so whenever this thing is, so this plus this is positive, so this term is positive, you find the condition that, putting this to this side, this is less than or equal to 8 pi g, the entropic force trace. So this, in case of a positive and sufficiently large entropic contribution, this could avoid recollapse. Instead of being 0, if this is positive, it might happen that this congruence of geodesics starts to expand, and there's a moment in which instead of reaching a maximum and recollapsing, as you would expect for normal matter that satisfies the strong energy condition, here you would have an expansion which keeps on running away, and it would produce an acceleration. So that's the origin at the microscopic level, if you want, of the cosmic acceleration. So let's see how this is looked at from the point of view of this entropic force and from the point of view of matter content. So a mechanical system, the usual Lagrangian in terms of the kinetic energy and the potential energy. The temperature is nothing but the gradient of the internal energy with respect to the entropy. This is du's TdS. In terms of hydrodynamical matter, rather than having point particles with some canonical coordinate q, here you have an energy density, which depends on both the entropy density and the metric, and the temperature, again, is nothing but the variation of the energy density with respect to the entropy density. Now, there's not just mechanical systems. You can do, in terms of the gravity sector, you could actually compute the temperature and entropy. We've learned from Gibbons, Hawkins, and York, and other sense that horizons also have an induced metric and an entropy. And you see this from the action of that three-dimensional. This would be the boundary of our universe, for instance. And you have to compute what is the extrinsic curvature, the trace of the extrinsic curvature in that three-dimensional surface. And this is the expression for a metric in Einstein with the 3+1 splitting. In the case of a Schwarzschild black hole, it's quite simple. You can compute what is the normal vector to that sphere at a radius r. It's given by this expression. From here, you can evaluate explicitly what is the extrinsic curvature and then do the integral. For instance, a square root of h times k is nothing but this expression. At the event horizon, r equals 2gm. So this would be 1 gm. And substituting this here and doing the integral, you end up with the action is nothing but the free energy of the massive object that we are describing here, the black hole. Now, we know that this quantity is the integral over the temperature times the entropy of that surface. This is the famous Bekenstein-Hawking temperature and Bekenstein-Hawking entropy. Okay, these are obviously two quantum origin quantities whose product is contributing to the action of the theory on the boundary. And this product is clearly, since it cancels the h bar, it's emergent in the sense that even though it had a quantum origin, its contribution is classical. There is no h bar here. If you make the h bar to 0 limit, you don't, this term doesn't disappear. It's still there. It's actually related to the mass of the object. Now we know that the contribution to bulk entropy of the black holes that fill up the universe, they could be from stellar evolution or they could be primordial, doesn't really matter. There will be an inevitable component of dark matter. Now, if these black holes, if this number is conserved and the number of black holes doesn't change, then the density dilutes like any matter component. It will dilute like a pressureless fluid. Its energy density will be proportional to their mass. Its entropy density would be proportional to their area, so m squared. And if you compute what is the variation in time of the internal energy, this is also related to the variation in time of the entropy, and both of these quantities are zero. So there is no contribution of an entropic force as long as the number of black holes are conserved and their mass does not change. Obviously, this changes if you have a large number of black holes that are accreting, so increasing in mass, or they're merging. If they are, then there will be a significant production of entropy, and therefore there could be an entropic force. We've made a computation, the quantity is not enough to explain the acceleration of the universe. That's why we went further. And we asked ourselves, okay, in the context of Freeman, Lemaitre, Robertson, Walker, so in the context of, say, a universe which is expanding, and I still keep my lapse function, your metric is given by this expression. This is the energy momentum tensor of an ideal fluid. If there are entropic forces, then the energy momentum tensor is not conserved, as I was describing. In using the second law of thermodynamics, either this or this, both give rise to an equation which is different from the usual continuity equation. This would be zero, and it will be zero in all cases in which the entropy is conserved in the expansion of the universe. But they're not zero here, because the variation of this quantity might have a contribution from the entropy growth, whatever the mechanism that generates the entropy, as I will describe in a minute. 4 minutes only. Okay, the Hamiltonian constraint gives you another quantity which gives rise to the Freeman-Raychaudhuri equation. This is the usual equation that tells you how the acceleration of the universe is decreasing, is negative, so it's decelerating, but this term could increase the acceleration. And I'm going to go rather quickly then, if I only have 4 minutes, into how this produces the acceleration in the case of a cosmological causal horizon. So here the tricks of the extrinsic curvature in this case is given by this expression. I'm taking the causal horizon distance to be a times the conformal time. Here you have an integral over time, so this is non-local in time. You know what the radius of that horizon is. You work out what is the Gibbons-Hawking entropy. You work out what is the temperature times the entropy, and therefore the density associated with it. Again, this is a merger, H bar, say numerator and denominator cancel out. And in this context, in this scenario where I envision this happening in a universe which is started in the false vacuum, so its Penrose diagrams described by de Sitter, it went through quantum tunneling, it produced an open universe inside which there's still some vacuum energy to drive inflation a certain number of e-folds until it reheated the universe. Not only did it reheat, it also made those hypersurfaces flat, sufficiently flat that today, after the CMB has been produced, so where we are here at lambda equals 0 without a cosmological constant in the late universe, any observer looking back would still see trajectories of light going along Euclidean curves. Now, putting the equations that I had before from the causal horizon, writing this matching at that edge and computing Hamiltonian constraint in conformal time, by redefining this quantity tau instead of conformal time, you find that instead of a lambda term, which would have appeared here, we have this sinh term that grows exponentially. And this gives you a very different behavior for the acceleration of the universe that matches lambda cold dark matter at high redshifts, at the CMB, and then very slowly starts differing from it at around redshift 0.83. It has a coasting point rather than 0.65 from lambda. It would have a different rate of expansion today. So it's essentially identical until today. It will be very different in the future. And you could compute in principle what is the effective equation of state for such a fluid when you define the fluid, but nothing but from the Hamiltonian equation, what is not the rate of expansion, so minus the matter and the curvature term. If you put all the cosmological observations that we heard from the previous session, CMB, logical structure, GAOs, rate of expansion, cosmic chronometers, and the supernovae, you get bounds which are in agreement for lambda cold dark matter, which gives you some chi-squared. And for this general relativistic entropic acceleration theory, you get chi-squared better than that of lambda cold matter by a factor of 4 in 1,000 degrees of freedom. But most importantly, the log of the bias factor, it's a factor 9 better for this model than for lambda cold dark matter. And I think this is the only instance of a theory where that happens. Now, with the same data, if you allow W0 and WA to be free rather than compare with lambda cold dark matter, you see that Grea predicts from the previous, from here, it predicts W0 WA, which differs from lambda cold dark matter, but nevertheless is much closer to the best fit. Maybe that's the reason why we get such a good chi-square. So Grea predicts this. Clearly, in the future, with Euclid, we've heard just a while ago, we should have all the tools to differentiate lambda cold dark matter from Grea theory. So to conclude and be on time, I've tried to convince you that this non-equilibrium phenomena in general relativity will induce an entropic force which could give rise to cosmic acceleration without having to introduce a cosmological constant. And moreover, the prediction of the theory is that future infinity is not de Sitter. It's Cry plus. It's not horizontal. It's actually a flat Minkowski space. I've only used quantum field theory, general relativity, and thermodynamics. I didn't have time, clearly, to go into the details of logical structure. I'm happy in the questions or even afterwards to discuss this. And I think that this could be, and I quote here, possible, because we have to test this with the best data we have today. It could be a possible solution to the H-naught tension. For the future, we leave what is the Big Bang contributing to the acceleration of the universe after inflation, when you have a tremendous production of entropy. And moreover, how does this cosmic web entropy, the fact that you start with a blob of gas, which start forming structure like galaxies, clusters of galaxies, all the filaments, the voids, how does this cosmic entropy that has been generated affect the dynamics of cosmic voids? And I'll leave here. Thank you.
Thank you very much.
I hope I've been sufficiently provocative, as Charlie asked.
Entropy to the particle horizon, right?
Yes, that's right.
It's equal to
the causal horizon.
I guess it would be the entropy coming from. It would be the. Thank you. Right. So it would be the area in Planck units squared.
Yes.
Right.
The only difference is that this depends on time.
Yeah.
Because since we're talking about a causal horizon, this means as the universe becomes older and older, the reason why, this is, by the way, resolves one of the questions of the coincidence problem. Why is it that the acceleration happens now? It didn't happen in the past. The entropy was not big enough.
Well, I think that's really fascinating. And I mean, it is provocative though, right? Because if it were a de Sitter space, then it would be.
There's no de Sitter.
I know.
I'm convinced.
In de Sitter space, we actually have actual radiation. This would be
the
entropy of the de Sitter radiation.
Here we go.
But here we're in the vacuum, and so the entropy is the entropy of what? It's the entropy of entanglement across.
Entropy of entanglement across that surface.
Oh, across that surface. Well.
It's really fascinating.
Thank you.
I meant to talk more, but just simply put this essentially it's an entropic force. It's going to alter the expansion history rather dramatically, but also we know probably it's going to apply to spherical like local systems as well. It has to. So will you comment whether this is going to violate Gauss's law or the equivalence principle, etc.?
Excellent question. Now, any modification of entropy which is sufficiently large has to come accompanied with a temperature. Typically, the temperatures that we have in laboratories for the amount of entropy that we produce in those systems, for instance, Brownian motion type of motion or dynamics, the temperature is very tiny and the contribution is negligible. However, there was this talk by, Valentine, yes, thank you, which got my attention because in the formation of galaxies, you also start with a more or less amorphous amount of gas, which ends up in a complicated spiral object. This object is clearly much more ordered than the initial gas from which it formed. This ordering must go somewhere. We have the idea in, say, in logical structure formation that when we consider those hierarchical formations of objects, the gas, which is there compressed, actually sheds out energy in the form of neutrinos and photons. Eventually, you have a thermonuclear reaction, which also produces neutrinos. Now, neutrinos and photons are relativistic, or essentially relativistic for the neutrinos, and they shed away not just energy, but also entropy. They are the the largest carriers of entropy out of the system. So this radiation of entropy out of the forming galaxy will leave an acceleration on the motion of particles in the potential wells of those galaxies. And perhaps, and it's something which back of the envelope calculation allows me to compute, the acceleration that was hypothesized by Milgrom to produce the modified Newtonian dynamics could come precisely from this kind of entropic force. If you do the computation, it has 1.2 10 to the minus 10, exactly. And this depends very much on whether the galaxy that forms is a very ordered spiral or it's a much more irregular galaxy. Therefore, those deviations that I heard might be understandable in terms of the actual entropy that was shed away from those subjects. So the more ordered systems should have a larger acceleration. And I'll close here. But anybody that wants to discuss, I'm happy.